Hello and welcome. In this lecture, we will have a look at how the three real mutually orthogonal unit vectors, which I had introduced in an earlier lecture, how you can use that set of three unit vectors as a basis for describing the polarization of electromagnetic waves. So we all are familiar with polarization. So polarization describes the definiteness of the fields in an electromagnetic wave. So for instance, if I have an electromagnetic wave, we know that it contains the electric field and the magnetic field components also. But if we are able to define how the electric field or the magnetic field is going to change with time, then that is called as polarization. We say that the light wave is polarized. So this is the set of real mutually orthogonal basis unit vectors. So let's say I have a plane wave which is traveling along the direction given as n cap. So this represents this plane. It represents the wavefront, and then we have two other directions, that is epsilon 1 and epsilon 2. So epsilon 1 could be the electric field could be along epsilon 1, and the magnetic field could be along epsilon 2, or the magnetic field could be along epsilon 1, then the electric field will be along minus epsilon 2. So we can use this to represent the motion of the electromagnetic wave, and then this actually becomes useful if you want to discuss. Suppose I have the wave, which is the electric field, which is in a specific direction, that is, in other words, it is polarized. How we can actually use this epsilon 1 and epsilon 2 to describe that. So now let's say the electric field is we have a plane electromagnetic wave which is represented by this orthogonal unit vectors, and then the electric field is along epsilon 1 direction, that is, I have the electric field which is along this direction. Then this epsilon 1 becomes the polarization vector. Okay, so epsilon 1 becomes a polarization vector, and then we say that the electric field is along epsilon 1. So we have some vector amplitude E naught, which is equal to some scalar times epsilon 1. Then if we know the electric field, we can always find out the magnetic field. So we really don't need to specify both electric and magnetic fields. Knowing one will automatically tell us what the other is, and so we know that the magnetic field is going to be along epsilon 2. So therefore the electric field can be written as epsilon 1 E1 e to the power I k dot r minus I omega t. So this is of course k dot r minus omega t, that is the phase of the electromagnetic wave, and the magnetic field could be written like this. So you can see electric field along epsilon 1, magnetic field is along epsilon 2. So this represents linearly polarized light, the light which is polarized along epsilon 1, and linearly polarized light, it is written as p state. Okay, so here even though I have written E0 over here, but then we are talking about electric field being along epsilon 1, so I'll represent that amplitude, the scalar amplitude, to be as E1 in this case, because we'd like to get a superposition of the two orthogonal polarization states. So it helps if I just use this notation here, so that's why I'm using E1 here. Then if the electric field is along epsilon 2, then epsilon 2 becomes the polarization vector, and the electric field can be written as E naught, which is equal to the vector amplitude is equal to epsilon 2 times some scalar amplitude, and the magnetic field in a similar way just have to multiply with root over mu epsilon naught. Whatever is the electric field amplitude, just multiply that with root over mu epsilon. So this from here we can get the electric field can be written in this way, and corresponding to magnetic field would be written like this. So this represents linearly polarized light, which is again p state along E2. So linearly polarized light along E1 and E2. So what it means is that you are already aware, if suppose I look at this, let's say the observer is somewhere over here, the observer is looking into the light. So linearly polarized light means if you look at the tip of the electric field, the tip of the electric field will lie in this on the same line. So the electric field is going to oscillate this way as it propagates. Now if epsilon 2 is the polarization vector, then the electric field is going to oscillate this way. So that's what we are talking about. So these are the two p states. One p state is along epsilon 1, and another p state is along epsilon 2. So E1 that is p set along epsilon 1 and p set along epsilon 2. So this is what we have. So just to be able to identify, so the polarization along epsilon 1 we call it as E1, polarization along epsilon 2 we call it as E2. So if you look at this, we have epsilon 1 and epsilon 2. So let's say this is epsilon 1 and this is epsilon 2. So E1 is along epsilon 1 and E2 is along epsilon 2. And we notice that because epsilon 1 and epsilon 2, they are orthogonal. That means E1 and E2 also will be orthogonal. So equation number 1 and 2, they represent linearly independent waves. And if we know E1 and E2, of course, we are not really bothered about the magnetic field because it's an EM wave, plain EM electromagnetic wave. We know the magnetic field can be found by the electric field in this way. In general, I could be 1 or 2. So if it is this electric field, then the corresponding magnetic field can be found by replacing I with 1, and for this one I with 2. So these two equations, that is equation number 1 and 2, we can now combine the electric fields that we have E1 and E2, because these two are orthogonal. That means they are linearly independent. So we can combine E1 and E2 as a linear combination to give us the most general homogeneous plane wave, which is traveling in the direction of k, and k is of course is along n cap. And this is given as just by simply taking a linear combination of these two waves, that is E1 and E2. So this gives us a general wave E, which is a function of r and t, as epsilon 1 E1 plus epsilon 2 E2, and this is of course the harmonic part. So let's call this as equation number 3. So of course here this E1 and E2, I'd like to just clarify here, this E1 and E2 here could be complex functions, because we are not only considering the direction, that is they are aligned at angles with respect to each other. These two orthogonal states, they are angled with each other, but there could be also we also have to allow for the fact that these two could have some phase difference. So to allow for this phase difference, so that's why in general we allow them to be complex functions. So then in such a scenario, that is from equation number 3, it is the magnitude of and phase of E1 and E2, these two vectors E1 and E2, because we are allowing them to be complex. So the magnitude and the phase of E1 and E2 will then determine the state of polarization of the wave. So first we will look at linear polarization, and then we'll have a look at the circular polarization. So linear polarization, or which is commonly called as the p state. So how do you get the linear polarization? We get the linear polarization if E1 and E2, they have the same phase. That is, either both of them are purely real or both of them are purely imaginary. So if that's the case, if both are purely real or purely imaginary, then equation number 3, it is going to represent a linearly polarized wave. So in space, if I see their orientation, so we have epsilon 1 along this direction, epsilon 2 along this direction, so E1 along this and E2 along this. So the resultant wave will be along the vector sum of E1 and E2. And these two are in phase, so they will change accordingly, proportional to each other. So this electric field vector, it is always going to, suppose I'm looking at this, the electric field is always going to oscillate along this line. So that's why linearly polarized state, or the p state. So the magnitude of the polarized wave, that's very straightforward, it's just basic trigonometry. It is under root E1 square plus E2 square. Then the polarization vector. So what is the polarization vector? Polarization vector is the vector, the unit vector along the resultant electric field, and this polarization vector, that is epsilon in this case, can be obtained using epsilon 1, epsilon 2, and knowing the magnitudes of E1 and E2. So epsilon 1 E1 plus or minus epsilon 2 E2 divided by the magnitude of the polarized wave. That gives us the polarization vector in this case. Then the polarization vector is inclined. What angle does it make? Sometimes we are interested in this, because suppose I consider a polarizer which has got a certain path axis. So if I align the path axis, say along epsilon 1, then I would like to know what is the angle between the direction of polarization and between the polarization vector and the path axis of the polarizer. So it helps to know what is this angle of inclination. So if we take epsilon 1 as the reference direction, then the angle of inclination is theta, and this theta is obtained using tan inverse of E2 by E1. So this is just basic trigonometry. So this shows that we can use epsilon 1, epsilon 2. It forms a basic set of basic fields, these two, for describing electromagnetic waves which are polarized in the p state. So for p state polarization, in general, the only requirement is E1 and E2, they have the same phase, either both real or both imaginary. So then they will be representing the electromagnetic waves which are polarized in the p state. So next we move on to circular polarization. Again, we'll make use of this equation number 3 here. So circular polarization, there are two states. So either you could be the electromagnetic wave, it could be tracing out a circle in the anti-clockwise direction, or it could be tracing out a circle in the clockwise direction to an observer who is looking into the wave. So based on that, there are going to be two states. One is an R state and L state. So R state is called as right circularly polarized, or R state corresponds to clockwise rotation of the electromagnetic field vector, and L state is left circularly polarized, which corresponds to a anti-clockwise rotation of the electric field vector. So when do we have circular polarization? We can have circular polarization if in equation number 3, these two the electric field amplitudes, these two amplitudes, they have the same magnitude. Okay, so E1 and E2, they have the same magnitude. So let's say that their magnitude is let's say E0. Okay, but here the condition is not just for the magnitude. Here they should also have a phase difference of pi by 2. So if E1 and E2, the two electric fields, the two orthogonal electric fields, if they have the same magnitude but they have a phase difference of pi by 2, then this equation number 3 is, we can write it in this way. Equation number 3, we could write it in this way. We could write it as E0 epsilon 1 plus or minus I epsilon 2 e to the power I k dot r minus I omega t. You can call this equation number 4. So how did we go from here to here? To understand this, the best way to do that is to expand this and see what happens. So let us consider a simple case. A simple case is the requirement here is that these two waves, they differ in phase by pi by 2. They have the same magnitude, but they differ in phase by pi by 2. So differing by pi by 2, we can allow them, if we allow one of these electric fields to be purely real, one of the amplitudes, okay, electric field amplitudes, if you allow them to be purely real and another one to be purely imaginary. So if one is pure real and another one is pure imaginary, then E1 and E2 will differ in phase by pi by 2. So if we plot E1 and E2 in the Argon diagram, this is what is going to happen. So we have E1 along the real axis and E2 along the imaginary axis. So the phase difference between the two, it is, I mean, this is like a phasor diagram. So the phase difference between the two is pi by 2. So if we have a scenario like this, the phase difference between them is pi by 2, then let E1 is equal to E2, E0. So because we have said that they must have the same magnitude. So let's say this electric field, the horizontal one, has got a magnitude of E0, and then E2 is going to be equal to plus or minus I E0, because we need to also take into account that the fact that this E2 could be in the opposite direction. So plus or minus I E0. So therefore epsilon 1 E1 plus epsilon 2 E2, that will be equal to epsilon 1 E0, E1 is E0, plus epsilon 2 E2, I replace it with plus or minus I E0, and that is going to give us, if I take E0 common, so epsilon 1 plus or minus I epsilon 2. So this quantity is going to become equal to this. So in equation number 3, so this quantity inside the bracket, we can just replace it with E0 epsilon 1 plus or minus I epsilon 2, and of course outside we'll have the harmonic term. So this is what equation number 3 it becomes. So now we can expand this equation number 4 by using the Euler's formula, which is e to the power I theta is equal to cos theta plus I sin theta. So we use that to expand the harmonic part. So expanding by Euler's formula, we have this first part will remain as it is. This first part that we have, it remains as it is, and this one we write it as cos of k dot r minus omega t plus I into sine of k dot r minus omega t. So that's the expansion that we get using the Euler's formula. So now just to simplify the scenario here, we will choose some particular axis. So let's choose the axis in such a way that the wave is propagating along the z axis. So the z axis is coming towards us. Then epsilon 1, we could choose epsilon 1 to be along the x axis. So epsilon 1 along the x-axis, epsilon 2 in that case will be along the y-axis, and n cap will be along the z-axis, because n cap is always the propagation of the wave. So wave is propagating along the positive z, so n cap is along positive z-axis. So epsilon 1 is along x, epsilon 2 is along y cap. So that's the setup that we choose here. In that case, what is going to happen is this quantity, that is k dot r, that is going to turn out to be equal to simply kz. K dot r is going to become equal to kz. So then this particular equation is simply going to become this, that is this epsilon 1 will replace it with x cap, epsilon 2 will replace it with y, and cos of k dot r will replace it with kz, and same thing over here also. So we have kz here in both the trigonometric terms. So now what we're going to do is we're going to use cos, so we're going to just open this up. We're just going to use the distributive property. So x cap I'll multiply with this, and y cap I'll multiply with this and this. So let's do that, and when we do that, this is what happens. So x cap multiplied with this, it gives us x cap cos kz minus omega t. Then x cap, there's a plus here, plus I x cap sine kz minus omega t. Then multiply this with this, so we have plus or minus I y cap cos kz minus omega t, which is this, and then we have plus or minus, we have I times I, which is going to give us I square. I square is minus, so when the moment we have minus, this plus is going to become minus and minus is going to become plus, so we'll have minus plus y cap sine kz minus omega t. So this is how we can associate. So if you take the upper sign, so we have to take the upper sign all throughout. So if we take plus here, then we'll get a minus here. If we take a minus here, we'll get a plus here. So this is what we have. So now once we have got this, so what we'll do is we'll collect the real part and the imaginary part. So the real part, we see that this is a real this is a real part, and this is a real part, and these two are the imaginary terms. So we will collect the real and the imaginary terms separately. And so we have E naught times we have cos x cap cos kz minus omega t, then minus plus y cap sine kz minus omega t. That's the real part, and the imaginary part will be I into x cap into sine kz minus omega t, and then we have one more, which is plus or minus y cap cos kz minus omega t. So this is what we have after separating the real and the imaginary parts. So we'd like to know what are the components of the actual field. So the components of the actual field, they are always obtained by taking the real part of the electric field. So we'll take the real part of the electric field, and the real part of the electric field, this is the x component and this is the y component. So Ex, which is the x component of the electric field, that is going to be equal to cos E naught, because the x component is whatever you're multiplying with x cap. So E naught cos kz minus omega t. So that's the x component, and the y component will be E naught times sine kz minus omega t. So we will combine them, and then we'll just call these two together as equation number 5. So equation number 5, it indicates that at a fixed point in space, the electric field vector has a constant magnitude. Okay, the magnitude is constant, but it sweeps out a circle. If you look at the tip of the electric field vector, it is going to sweep out a circle, and it is going to do that at a frequency of omega. So if we have, let's say, if we take, because here there are two possibilities, so we have considered this to be epsilon 1 plus or minus I epsilon 2. So we have two possibilities, either epsilon 1 plus I epsilon 2 or epsilon 1 minus I epsilon 2. So these are the two possibilities. So let's take the first possibility. The first possibility is epsilon 1 plus I epsilon 2. Then we find that the electric field will be seen to be rotate anti-clockwise. That is, if you look at the source, the electric field will seemingly rotate in the anti-clockwise direction. And how this happens, we can actually understand this. Just you need to do this only once to satisfy your curiosity. So let's take the scenario here. So we have the electric field. So we're going to consider, this is, by the way, this is called as the L state. If I take epsilon 1 plus I epsilon 2, it's called the L state, or it's a left circularly polarized state. In optics, it's called as a left circularly polarized state, or L state, and in modern physics, it's called as the positive helicity. So this is the L state that we are talking about. So we can understand this, that this electric field, as time progresses, this electric field, the tip of this electric field is going to trace out a circle in the anti-clockwise direction. So we can understand this, just we need to work out only once. So this is the basis vector that we have chosen, epsilon 1 plus I epsilon 2. This is a combination of basis vectors that I have chosen, epsilon 1 plus I epsilon 2. So because we have epsilon 1 plus or minus I epsilon 2, I have chosen the upper symbol. So that's why we have epsilon 1 plus I epsilon 2. So this will imply that Ex is going to be equal to E naught cos kz minus omega t, and Ey is going to be minus E naught sin kz minus omega t. So how did we get that? We can get that from here, because I have chosen here the upper symbol. The upper symbol is the plus. The moment we have the upper symbol, then here we have to choose the corresponding upper symbol everywhere. The upper symbol here for the y component is minus, so that's why we get a minus sign here. So epsilon 1 plus I epsilon 2 will correspond to this to be the x component, and the y component will have a minus sign, minus E naught sin kz minus omega t. Now we are only interested in how this rotates, how we are only interested in how this electric field vector, how it rotates in the anti-clockwise direction. That's all we want to see. So it really does not, we can just get rid of this z dependence, because the way by which we can see how can we see the rotation of the electric field vector, we need to choose a fixed value of z. The z axis is coming towards us, so we need to choose a fixed value of z, and at that fixed value of z, we will, let's say by some means we are able to measure the electric field, then in which direction will it show the electric field at different times. That's all we are interested in. So it is immaterial which point z that I choose, because all the points, all the different wavefronts on the plane wave, they are exactly identical to each other. So I can choose any z value that I want. So if I can choose any z value that I want, let us choose a z value which is going to make things simple. So we choose z equal to 0, and the moment we choose z equal to 0, ex is going to become this. So we have a minus cos of minus omega t. Cos minus theta is equal to cos theta, so we have ex equal to E naught cos omega t, and here this becomes 0, so we have E naught sin minus omega t. Sine of minus theta is minus sin theta, so that minus and this minus will cancel out, and we'll have plus E naught sin omega t. So these are your x and y components. So now with this x and y components, we can go ahead and we can obtain what happens. We can see what happens as this time progresses. So let's make a table. It helps to make a table. So we'll make a table of omega t, ex and ey. So when omega t is equal to 0, so in that case ex will take the value E naught, because cos omega t is equal to 1, so we'll have E naught, and ey is going to take the value 0. So that means we are going to have the wave which will be over here at this point. Okay, so now next what we do is we see what happens when it has progressed 1/4 of a cycle. 1/4 of a cycle means omega t is equal to pi by 2. So if omega t is equal to pi by 2, then cos of pi by 2, that is going to give us 0, and sine of pi by 2, that is going to give us 1. So we have 0 and E naught. Okay, so this is what it is. So 0 and E naught, that's going to be somewhere over here. X component is 0 and y component is positive, and when that happens, so next one will be over here. That means the wave has actually moved in this direction. The wave has actually propagated in this particular direction. So this is the direction in which the wave has propagated. Now let's consider the next one. So at omega t equal to pi, that is half the cycle has passed by, and half the cycle has passed by, then from here we'll find this ex will be equal to minus E naught, and ey is equal to 0. That means the wave has propagated in this direction, and it has come over here. So it has moved in this direction. Then next we'll consider this to progress one more quarter cycle. So when one more quarter cycle, does ex is 0 and ey is minus E naught. So that means we are talking about this point here. So this point, when we progress, the wave progresses this way. So the wave has traveled. So that means the electric field, the tip of the electric field has traveled this way. And finally, when it has come full cycle, then again E naught to 0. That means we are back to this point. Comes back over here. So we can see here it has gone through one full cycle. It has gone through one full cycle in the anti-clockwise direction. So we can say that in this case the wave is going to travel the electric field vector, this is going to travel in the anti-clockwise direction. So this anti-clockwise motion of the tip of the electric field vector, that's what the L state is all about. So in a similar way, if we take the negative sign epsilon 1 minus I epsilon 2, then the electric field is seen to rotate clockwise when we are looking at the source. And again we can perform a similar exercise as here. So here we are considering epsilon 1 minus I epsilon 2. So we are going to take the plus sign because plus sign appears below. Then considering k is z equal to 0, so we will have minus E naught sine omega t. And then here also we can go by the same way, take the different points here. So at the starting point we'll have here the electric field will be somewhere over here. Next, after 1 quarter cycle, the electric field is going to be over here. So it seems to have traced out a quarter of a circle in this direction, in the clockwise direction. In a similar way, it travels this way. So we have a wave which has propagated, and the tip has moved in this direction. Similarly, another quarter cycle, the wave propagates till here. One last quarter cycle, the wave propagates this way. So this gives us clockwise motion of the tip of the electric field vector. So we find that the electric field vector rotates in the clockwise direction like this. This is a clockwise direction, that is the anti-clockwise direction. So here the electric field is going to rotate in the clockwise direction like this. So now actually this makes it more useful if we introduce a new set of complex orthogonal unit vectors. Okay, but before that, for the sake of completion, so this is going to be, this is called as right circularly polarized light in optics, or R state, or it is called as negative helicity in modern physics. So now it makes more sense if we introduce a complex orthogonal, a set of complex orthogonal unit vectors, and we construct that unit vector, those unit vectors in this way: epsilon plus minus, which is equal to 1 by root 2 epsilon 1 plus or minus I epsilon 2. So both of these unit vectors, that is epsilon plus and epsilon minus. So we can see here this epsilon plus. So the way it is defined, epsilon plus will be equal to, you just have to take the upper symbol. So we have 1 by root 2 epsilon 1, and then we'll have to take the upper symbol, which is plus I epsilon 2, and epsilon minus we'll have to take the lower symbol. So that's how we find out. So this is actually a set of two vectors that we have defined, and these are complex unit vectors. So these have these properties. The first property is, if you take the dot product of the conjugate of epsilon plus with epsilon minus, or the dot product of the conjugate of epsilon minus with epsilon plus, that will be 0. The second property is, if you take the dot product of the conjugate of epsilon plus with epsilon plus itself, or the conjugate of epsilon minus with epsilon minus itself, that is going to give us 1. And thirdly, the dot product of the conjugate of either of these two with the n cap vector is going to be 0. And we can immediately recognize this from our basic understanding of vector spaces, that this is simply, we are just finding the inner product of these vectors. So whenever we have plus minus taken, when we take the inner product of plus or minus with the other vector which is of the opposite sign, that is going to be 0, and plus if we take it with the same sign, that is going to be 1. And of course both of them are perpendicular to the n cap vector, so they are orthogonal, so that this scalar product is always going to be 0. So you can actually verify all of this. You just need to do it once. So let me do it for the first one. So it's really straightforward. All I need to do is, let's say I want to verify this first relation, that is epsilon plus. I want to take epsilon plus, the inner product of epsilon plus with epsilon minus. So inner product of epsilon plus with epsilon minus. Now inner product, because this is the function on the left side, we have to take the conjugate. So epsilon plus star dot epsilon minus. Now epsilon plus and epsilon minus are d's, so we can just substitute this. So 1 by root 2 is going to give us 1 by 2, and this epsilon plus, we are taking conjugate, so epsilon plus conjugate. I'm afraid there's a small error here, pardon the error here, so this should be minus. Extremely sorry about that little error, so we'll have a minus here. So epsilon, and so because we are taking conjugate of this, so we'll get a minus sign. So now what you have to do is just open this up. So when we open this up, we'll get these 4 terms, and what's going to happen is this is going to be anyway 0, because epsilon 1 and epsilon 2, they are perpendicular to each other, and this is going to give us 1, and this is going to give us 1, so 1 minus 1. So overall, which is going to give us? It's going to give us 0. So this proves one of these results. So you can just try out the rest on your own. So it's really straightforward. All you have to do is just expand them. And this equation number 3, that is, okay, so this is equation number 3. So we can rewrite equation number 3 more conveniently using epsilon plus and epsilon minus, and we can write it in this way: epsilon plus E plus epsilon minus E minus. So here E plus and E minus, they are complex amplitudes. In general, they are complex amplitudes. So using this, we can actually now represent the polarization state, the various polarization states, using epsilon. This set of basis vectors, we can represent different polarization states. So if epsilon E plus and E minus, they have the same magnitude and the same phase, then equation number 7, that is 7, this would be equation number 7. Yes, that was the error in. So this would be equation number 6. Extremely sorry for the goof up in the numberings. So this is equation number 6, and this, let's call it as equation number 7. So equation number 7. Okay, so then equation number 7, it represents a p state. So for p state, all we have to do is this E plus and E minus, they have to be of the same magnitude and they have the same phase. That is, either both of them are real or both of them are complex. That is p state. Then how do you get R state and L state? That's very straightforward, because if you want R state, all we need to do, if you want R state, we just need to make E minus to be non-zero and E plus to be 0. So that is going to give us R state. And if you want L state, we need to make E plus to be non-zero and E minus to be 0. So that's hence the term positive and negative helicities. So we can represent R state and the L state. We can represent P state using this, and any other combination, we'll have the elliptically polarized light, that is the E state. E state is basically the tip of the electric field vector. Instead of tracing out a circle or a line, instead of tracing out a circle as in this case, or tracing out a line, it traces out an ellipse. So that is an elliptically polarized light, or the E state. So if E plus and E minus, they have different magnitudes but the same phase, then equation number 7, it represents elliptically polarized light but with principal axis along epsilon 1 and epsilon 2. So we could have something like this. So let us say we have, this is one direction, this is another direction. So we have epsilon 1, let's say here, and we have epsilon 2 along this. So if E plus and E minus, they have this different magnitudes but they have the same phase, then we will have elliptically polarized light with the principal axis along epsilon 1 and epsilon 2. So we'll have something like this. But on the other hand, if we have different magnitudes and different phases, then in general that is going to be in some random direction. This is going to be the direction of polarization. It will be elliptically polarized way, but it will be in some random direction. So if this is epsilon 1, and let's say this is epsilon 2. So this is going to be the envelope, this is going to be the tip of the electric field vector. It's going to be in some random elliptical direction. So that's the general elliptical state. So epsilon plus and minus, it's really helpful because it helps us to describe all the different polarization states of a plane electromagnetic wave. So to summarize, we have different polarization states for electromagnetic waves. We have the P state, the L or R state, these are the circular states, and or the E state, which is more general. So two sets of orthogonal unit vectors can be used to represent any of these states of polarization. So we could use a linear polarization basis, or we could use a circular polarization basis. So the relationship between these bases, epsilon 1, epsilon 2, or epsilon plus, epsilon minus, this is the relationship between these bases. So if we could take, let's say, the linear polarization basis, that is epsilon 1 and epsilon 2. If we take the linear polarization basis, then the general wave equation will be epsilon 1 E1 plus epsilon 2 E2, and then the harmonic term. You can compare that with the circular polarization basis. So circular polarization basis, the electric field is going to be E plus epsilon plus E plus epsilon 2 epsilon minus E minus. So you can see the similarity in which we are writing the electric field vector. Then E1 and E2, if they are in phase, E1 and E2, if they are in phase, then we get a P state. If E2 is 0, then we get a horizontal P state. If E1 is 0, we get a vertical P state. If both of them have the same magnitude, then the P state will be at 45 degrees. That is linearly polarized light, which is at 45 degrees. Then if E1 and E2 they have an arbitrary phase difference, then we get an elliptical state. If E1 and E2 have the same magnitude but they differ by plus pi by 2, we get the L state. And if they have the same magnitude but this time they differ by minus pi by 2, we get the R state. Similarly, in circular polarization basis, here E minus is 0, we get the L state. E plus is 0, we get the R state. E plus or minus, they have the same magnitude, we get the P state. If the phase difference is 0, we get horizontal phase, P state. If phase difference is pi, we get a vertical P state. If phase difference is pi by 2, we get a P state at 45 degrees. And finally, if E plus and E minus, they have different magnitudes. That's all. No other condition on phase. They just need to have different magnitudes. Then we get, in general, we get a E state, the most general E state, the elliptical state. So this summarizes how we can use this unit vectors, the different unit vectors, the unit vector basis, as E1 and E2, epsilon 1, epsilon 2, and epsilon plus, epsilon minus, to define in general any polarization state of an electromagnetic wave. So in the next lecture, you will be familiarized with an easy way to determine the state of polarization, because it's all of these this theoretical constructs that we have devised over here. These theoretical constructs they depend on measurement of the fields, whereas it's much easier to measure the intensities of electromagnetic waves. So we, instead of using electric fields, if we can find some way to measure the intensities of the waves, then we can then we should be able to find out the state of polarization, and the way to do that would be using what are known as Stokes parameters. So that's what you will be getting familiar with in the next lecture. So with this, we come to the end of this lecture. Thank you.